All right, so we'll move on now with talking about the geologic time scale and land formations and so forth. So one aspect of the geologic time scale is that it's almost incomprehensibly long, right? The duration of our lives is very, very short compared with the duration of time that the Earth has been in existence. So this table here is showing, let me turn on my pointer. Okay, so this is showing different eons here, and then eras, and then within each era there are different periods, and then within the periods there are different epochs, at least for the Cenozoic era. And the far right side shows the boundary dates in MA, millions of years, right? So the Earth is 4,600 million years old, right? So 4.6 billion years old. Then if we look here within the Cenozoic, we have the Quaternary period, which is divided into the Holocene and Pleistocene epochs. So the Holocene is 0.012 million years until the present. So that's about 12,000 years, right? So the time we're living in is the Holocene, although there is some debate about whether we've entered a new geologic epoch called the Anthropocene, which is characterized by the fact that humans have had such an impact on changing the surface of the Earth, cities, changing climate, and so forth, that we've actually left the Holocene. But anyway, I'll stick with this table. We are in the Holocene. The Pleistocene is the epoch that came immediately before that, and that's from 12,000 years to 2.6 million years. So you'll notice that these two have the same height, right? The cells themselves are the same height. But the Pleistocene is really much, much longer than the Holocene. So none of this is to scale. And then we get into tertiary periods, which is Pliocene, Miocene, Oligocene, Eocene, and Paleocene. And then we get into the older eras, Mesozoic, which is Cretaceous, Jurassic. We've all heard of the Jurassic period, right? Because of the movie Jurassic Park. Then there's Triassic. And then, of course, there's the Paleozoic and older and so forth. All right, now I'm not going to expect you to memorize this whole table or anything like that. I just wanted to show it because it really does show how long the Earth has been in existence and how short the current epoch is that we're living in. So as geotechnical engineers, we pretty much restrict ourselves to dealing with quaternary sediments. Okay, we focus primarily on soils, sand, gravel, silt, clay. Those things become sedimentary rock over time. So by the time you get into the tertiary period, we're dealing primarily with rocks, right? The soil has become sedimentary rock by that point. Maybe not in all cases, but that's just kind of a general rule of thumb. So the kinds of soils we're worried about are in the quaternary period. And actually, by the time the soil is fairly old, if it's from the Pleistocene epoch, it's probably stiffer and stronger and a bit cemented compared with soil that's brand new from the Holocene, right? Holocene alluvium, for example, tends to be very loose. It can be soft. It can be problematic. So understanding which of these epochs we're in can be really important. And it's kind of ironic, but for geotechnical engineers, Pleistocene is old, right? If the soil is Pleistocene, that's what we'll look at how far up the scale that is in terms of these eons and eras and periods. You know, we're dealing with really, really young materials for the most part as geotechnical engineers. We will get into tertiary rocks and so forth. Sometimes there are landslides that happen in these rock formations. And so it's definitely possible that we'll start getting into tertiary or older materials as well. But it's really the quaternary and especially the Holocene materials that cause problems for us and that we're the most concerned about. All right, let's look at some of the surface processes that shape the Earth. So there's weathering. Okay, that's where rock breaks down. And if it weathers in place, it's residual soil or residuum. Okay, and the reasons rocks break down can be that heat and cool cycles cause them to form cracks due to the stresses that develop in the rock as they swell and shrink. Then water can get in those cracks, ice can form and further push those cracks apart, chemicals can get in there and start chemically weathering the soil. So because of those reasons, you can get residual soils. And what's in the residual soil depends on what was in the rock from which it weathered. So oftentimes it's clay minerals that are residual, but not always. Okay, and then there are gravity surface processes. So this is gravity deposition or slope wash. Those soils are called colluvial. We actually have quite a bit of gravity weathering or gravity erosion that's happening not far from here in the San Gabriel Mountains. Those mountains are being pushed up at actually a fairly rapid rate by geologic timescale considerations because there's a bend in the San Andreas Fault. So as the two plates are sliding past each other, the San Gabriel Mountains are getting pushed up by that bend in the fault. And as those mountains get pushed up, the material that's kind of weathered will flow downhill under gravity processes. And then if there's a heavy rain event, that will really wash the soils down and you can get debris flows. So that would be fluvial, right? That's when surface water flows. Stream or river deposition is called alluvial or alluvium, right? So if the material was deposited by water, we'll call it alluvial. Then there are marine and coastal processes, wave erosion and deposition and so forth. There's also when a stream carries sediment out into the ocean. The soil, in the stream was carried in suspension because the stream was moving. When it hits the ocean or the bay or whatever is out there, the water is very still and the sediment can kind of settle out and form soil that way. And those are called marine deposits. There's also deposition in lakes, right? Streams flow into freshwater lakes or saltwater lakes. And those materials are called lucustrine. And then there's ice surface processes. So this is deposition associated mostly with glaciation. So glaciers have a way of really carving rocks. You may have been to Yosemite, right? Glacial valleys are often really beautiful places to go. And then there's deposition by wind. So these would be sand dunes. They're called eolian soils. And then there are volcanic soil deposits and rock deposits too. And then there are materials deposited by human activities. So if you want to go and develop a new site, the ground may not be very level and it may not be well suited to just go and build directly on the site. So you may have to place some fill. So that's often called artificial fill. And artificial fills are often the most problematic soils because geologic processes often make soils fairly dense and strong. Whereas we don't do that. We tend to make them, we try and do a good job of compacting the soil, making it dense, but it's hard for us to make it as dense as geologic time can do. So let's look at a couple of slides here that show different forms of landslides. This form of a slide happens when it's a rock fall. So you have a rock that was attached up here, and then maybe there's a plane of weakness, and boom, it falls and it breaks apart and sends cobbles and boulders flying. There's also rock toppling. So rock masses generally are not completely intact. They're going to have joints and fractures, discontinuities in the rock. And actually the strength and behavior of rock is pretty much entirely controlled by those discontinuities. An intact rock mass is really strong and stable, but if you start having these joints, you can get these problems happening. So a topple happens when the joints tend to be oriented as shown in this figure. So they're not going to slide down into the earth along those joints, but they are going to kind of just topple over like what's shown here. And then here is a landslide. This is a deep-seated landslide where probably you have some soil, could be rock. Basically the shear strength of the soil was inadequate, and then the slide mass moved downhill. These often are happening as a result of water being present in some way. As we'll learn later, water has two effects on soil. It makes it heavier and it makes it weaker. So that's a kind of a double whammy that can result in landslides. All right, this one is a spread. This is where you have some fairly intact weathered rock here, and it becomes more and more weathered as you move away, and as it gets weathered, it gets weaker, and so it tends to have these slope failures that make it spread out. And then this one is a flow slide, so this is generally fairly shallow, often triggered by heavy, intense rainfall. So the water flows down, or it comes down on the slope and erodes soil away, and it flows to the bottom and can cover houses and things like that. We do have debris flows like this in LA because we have tall mountains that are susceptible to rainfall-induced erosion, especially after wildfires. Okay, when the vegetation burns, it makes the soil hydrophobic, the water hits the slope and it erodes all that stuff down. So after there's a big wildfire, we have to be really cautious about the possibilities of these debris flows happening. All right, this is a slide that shows alluvial processes for a river that's flowing through a floodplain. So the whole floodplain would be like this whole thing, right? That the floodplain is where the river is doing its thing, moving soil around, depositing soil. And what you'll find most of the time is that rivers don't flow in a straight line, right? They tend to flow in these S-shaped patterns. And then here's one of the patterns, or one of the S-shapes right here. If you think that the amount of flow is constant at all points in the river, then the water is flowing more quickly along the outside, simply because it's taking a longer path around, and slower on the inside. So what tends to happen when the water is flowing slowly is that soil gets deposited or accreted, and it forms these point bars. So if you see the S-shaped river, the point bar is younger material. Okay, it's been deposited more recently. It's probably looser, and more susceptible to deformation and weakness. And then as the water flows here, it's actually cutting this bank because it's flowing faster. So it's eroding out this way. This bank is kind of moving that way. And so the cut bank is often stronger and stiffer material because it's been there longer. It's now being eroded. Sometimes you'll get these bars in the middle of the river, right? Channel bars. And then a lot of the time you'll get these little meander scars here. This just means the river used to go right there, right? And it left a footprint. It left some evidence that the river used to be there. And then sometimes you'll even get an oxbow lake. That's where the river maybe used to go this way, and then it flooded over its banks and moved over here, right? But it left behind this little lake in the back. Okay, and this is what I was talking about before. You get deposition along point bars, erosion on the cut slopes. So this is important for us because if we want to study liquefaction, say following an earthquake, we know that point bars are more likely to have liquefaction than the cut slopes on the other side of the river. So it's an important aspect of alluvial geology to keep in mind. One aspect of rivers is that they tend to build up natural levees. And so here's the river, it's carrying sediment. If the river gets too tall and starts flowing over the banks, some of that sediment will get deposited right there. It tends to be the coarser, heavier sediment that is carried along if the river is moving quickly, but when the water starts flowing over, it's not moving so quickly, and so those sediments get deposited. And then the more fine-grained sediments flow over here to the back swamp. And so these would be silts and clays, and oftentimes you have plants growing there and they get mixed up with silt and clay, so you get this kind of mix of organic and inorganic soils. So plant material mixed together with silt and clay can be really soft. So these swamp deposits can be, very compressible and weak. And then, the river eventually, it's depositing material along its bottom and on these natural levees. And it actually is higher than the back swamp most of the time. So it's not a very stable situation, right? Eventually the river grows and grows and grows, and then it's not stable for it to stay along that pathway anymore, and it'll start flooding over here instead. So a little more alluvial geology. Okay, and then there are alluvial fans that form. This is a cross-section of an alluvial fan. That's where water flows out of the mountains and carries heavy particles initially. This would be cobbles and gravel. And then eventually the land starts having a gentler slope and you start getting finer and finer materials deposited. So maybe these are cobbles and boulders. This might be gravel. Then you start getting coarse sand, medium sand, fine sand. By the time you get down here, maybe you're starting to get some silt and clay. So here's a picture that shows an alluvial fan. Okay, all this material clearly came through this stream and it gets deposited. There's the fan right there, right? And that river just keeps delivering material there. And then this is obviously a big braided river showing the active floodplain deposits as well. Okay, we also have marine landforms. And if you're interested in coastal engineering, you should take Professor Galen's course. So anyway, we get these berms. You know, a lot of the time we're dealing with sands here at the beach. And then there's a bluff or escarpment. Here's the pub. One thing you'll find in the textbook is that they put in a lot of jokes. Sometimes they're funny, sometimes they're not. But anyway, here's the pub on the back side of this scarp. So this is protecting the pub from flooding. If there's a big storm, you know, the waves break against this, and the intention is that it doesn't come here where the people are living. But you'll get these bars forming, and as the waves hit the bar, they form breakers and so forth. And then here's the beach and berms and all of those sorts of things. All right, glacial processes are really important at forming the surface of the Earth. During the Pleistocene, there was an ice age, and so the transition between the Pleistocene and the Holocene was characterized by the end of the last ice age. So that's when glaciers were melting and retreating, and you know, a lot of water was flowing on the surface of the Earth at that time, carrying sediment. So during the ice age, there's all these glaciers that are grinding away at the rock slowly and carrying all of that out into this wastage area. So you get the front end of a glacier doesn't look very pretty. It's a mix of ice and rock, whereas this part might be more blue, or a lot of the time glaciers are so compressed that the ice looks blue. But anyway, this is the glacial process. And here's a glacial valley. You'll see these kind of U-shaped valleys form where there was a glacier that had initially been in here. And over time, that glacier has eroded away all that rock, right, and formed this valley. And of course, here's Yosemite, big glacial valley, and you can see that U-shape, right? And you can see El Capitan, Half Dome back in the distance. So you get some pretty amazing formations from the action of these glaciers. All right, then there are eolian landforms that are from windblown sands, typically. And you'll get these zones where the wind is blowing and carrying away soil. So there's no vegetation. That means it's more erodible. And also, since it's more erodible, the sand is being eroded and there's no time for plants to form. Over here, it's vegetated. That means that it's probably not as erodible. Sand's not being carried away. Then the sand gets blown and it'll blow up against a dune, right? So here's a sand dune. If the wind is blowing pretty fast, right? So if the sand hits this dune and gets deposited, it's been like a projectile, boom, it hits it pretty dense. So the density of sand is directly related to depositional energy. Sands deposited at high energy tend to be dense. Sand deposited at low energy is loose. So when the wind blows up over the dune, it kind of has these eddy currents that go like this, and then deposits loose sand on the backside of the dune. So you end up with dense material, loose material, and then these sand dunes often move all over the place in the desert due to wind events that happen. So here's a migrating dune, just showing how it moves. Okay, there are also tectonic processes that happen that can really have a big impact on the form of the Earth. So here's some folded structures, right? You can see how it's like a sine wave of these rock structures. So this might happen where the plate is being compressed and it causes the soil and the rock formations to buckle. And then these soil and rock layers get eroded. So here you can see another one that used to be there. This one used to come up here and maybe connect up with another one, but it's been eroded away. So you can see the tectonic processes at work here. And you get these domes that form, right? So here's old material and then younger material and then younger material still, because it's formed a dome. And like here's what the dome would look like without erosion. After it's eroded away, you can see all the layers of the dome, just like you're peeling back an onion or something like that. This one is showing a fault block. So this valley is formed by normal faulting. And this would happen in an extensional zone where the two pieces of crust are being pulled apart and that block in the middle is just moving down, right? So the direction of slip would be that this is moving down this way and then this block is not moving that way. So you get shear acting downward on this side and upward on that side. And then There's also really complex structures. So here's like a strike slip fault, and you get all these bends and folds. So this is kind of like how California is. We have a lot of active faulting, very complicated bends and folds in our rock units. And it can make it really complicated to try and interpret. You know, oftentimes you'll get older material that's thrust up over younger material due to tectonics. So in general, you would have young material on the top and older material as you go down, right? If it's formed from sedimentary processes. Well, that can be disrupted if it's formed and then subsequently moved around or uplifted over. Okay, and here's a fault scarp. So this is, here's the fault. You can see it right there. This is after it's moved. So this one has a significant dip slip movement. So the dip of the fault is this direction. The strike of the fault is that direction. Faults can have both dip movement and strike movement, right? So that would be oblique. They can move in both directions. If it moves in the dip direction, you can kind of match up the soil layers and figure out how far it's slipped. If it moves in the strike direction, it's harder to do that. You can still trench the fault and kind of look at that, but it's harder to see strike movement just because the soil layers are still aligned with each other. All right, so this is what it might look like right after an earthquake rupture happens. You have this very clearly defined fault scarp. But then over time, that will get eroded away, right? Rainfall will land here and it will run over the face and erode it. And so this is a kind of geomorphology that a geologist might look at and say, oh, look, there's a fault right there. Whereas you can't see it anymore, really, right? But they know what they're looking at. So that's how you can see geomorphic evidence of earthquake faulting. Then here, this is showing normal faulting, where one block moves down relative to the other. This is reverse faulting, where that block moves up, right? So the Northridge earthquake happened on a reverse fault, and then strike slip fault, where they just move horizontally past each other. So this is, strike slip is like the San Andreas fault, a transformed plate boundary. This is a set of satellite and aerial images showing the fault rupture for the magnitude 7.1 earthquake that happened on July 5th, 2019, up near the town of Ridgecrest. So it's showing before and after, before, after. So the before one is a little more colorful picture, and then the after one clearly shows the fault rupture right through here. And you can see that this block of land has moved to the right relative to the lower block of land. Or alternatively, if you were standing over here looking this way, this block of land has moved to the right relative to this block of land. So this is a right lateral strike slip movement. Okay, if the land on the other side of the fault looks like it's moving to the right, that's right lateral. That's how the San Andreas fault moves. This is not the San Andreas fault, it's a different fault, but that's the nature of the movement. And you can see how it's broken the road right there, right? So it ruptured right across the roadway. The road had to be repaired quickly to facilitate people getting, through here. Here's another one that didn't rupture a road or anything, but these are pretty fascinating images just to show the nature of how the Earth moves and how these sorts of tectonic events can change the Earth's surface. All right, that's all for this lecture.